scores. It looked like everybody seemed to understand this already, but we'll go through and do it real quickly. Temperature is a measure of the average kinetic energy of all of your particles moving around within a sample. Heat is a measurement of the total energy within the system. So you could have several different containers at the same temperature, but would do varying amounts of damage to your skin if they had been splashed on you. Okay, the exam question asked about a drop of coffee versus a cup of coffee, okay, in the reference to heat and temperature. If they're at the same temperature, okay, do they have the same capacity to burn you? No, because it's the amount of that exposure that you're seeing. Okay, temperature is just an average reading through the sample. It doesn't tell us how much there actually is. Okay? When it comes to temperature, we have 3 different scales, just like every other freaking unit system we've got. We've got different ways of measuring it and monitoring it. They're all coming back to kind of the same idea. We're looking at how mercury moves through a closed system. Okay? The higher the temperature, the more energy our particles have. The more energy they have, the more they move. The more they move, the higher up that little sample they become. Okay? Or that tube. So within our 3 systems, we've got Fahrenheit, which is again referenced as English, Celsius, which is the most widely used, both in science and in the world. And then we have Kelvin, which is used strictly in science. Okay? All of those can report or observe the same thing, but they have different uses for when we would go through and use them. Fahrenheit is kind of our arbitrary scale. Someone went through and picked out some numbers. They picked 32 degrees, okay, for the temperature of freezing water. And they picked 212 to be the point at which water boils. So it's all based off of water. Why did they pick 32 and 212? That's probably as good an answer as I would come up with. They felt like it. That's an arbitrary system. They just established it and went with it. Celsius, similar concept. We picked some kind of arbitrary numbers. We picked our freezing point to be 0, and then we picked our boiling point to be 100. Why might Celsius be a little bit easier to work with? It's an easier scale if we consider what things we would most commonly use, like water. Freeze, 0. Boil, 100. Relatively simple numbers to work with, as opposed to 32 and 212. Okay. Why do we still use the Fahrenheit? For the same reason we use a whole bunch of other random units. Some old dead person insisted or beat up enough people that we continue to use it. Kelvin. Okay. The Kelvin scale was invented or created relatively recently. In this case, if we look at our freezing point, water freezes at 273 Kelvin and boils at 373 Kelvin. An interesting thing to note is that it is technically written up there wrong. It is not degrees Kelvin. It is strictly Kelvin. There is no degree symbol. The degrees is an artifact of how we measure Fahrenheit and Celsius. Kelvin is an absolute temperature scale, which comes from monitoring motion in a sample. And if we drop all the way down to 0 Kelvin, what happens to our motion? It stops altogether. Okay? Which means we can't ever achieve exactly 0 Kelvin, but we can get darn close. Okay? Why would we invent Kelvin as a scale instead of using Celsius or even, for that matter, Fahrenheit? What about absolute 0? Why is absolute 0 valuable to us?
Because it's theoretically the coldest we can possibly get.
True, but why not just say, what do we get? Negative 273 degrees Celsius. That is absolutely coldest I can get too. Why not stick with that value? Why invent a new scale? There's actually a sound reason behind it.
Calculations?
What about calculations?
With Kelvin, there's no calculation involved. The number is what it is.
Not quite.
So you
It's negative sign. That's all it is. In the Kelvin scale, there is no negative number. Okay? In degrees Celsius and Fahrenheit, there is a negative number. By putting that negative in there, that can make our calculations much, much more difficult and sometimes impossible to conclude properly. Our Kelvin scale drops that onto an absolute system where I don't have to worry about the negative. Okay? That cleans up all of the calculations very, very nicely.
So I don't really just use Kelvin.
If I told you it was 273 Kelvin out, what would you do?
No, I have no idea.
And if we
Okay.
used it for
Number one, you might say you have no idea. Number two, if you heard 273, you'd probably be panicking.
Well, I mean, if you integrate it, use
just
the
a
law.
train of thought, I mean,
So
if you used Kelvin for years, it,
if we
Yeah,
pick
you're
up
used
and
to it.
develop a system and use it, then it would be consistent. And that, unfortunately, is not going to happen.
Okay. Well, that's why we're not using Celsius.
That's why we're not using Celsius. That's why we're not using meters or liters or any of those other units. Okay. Take it a step further. Remember, we're looking at science developing over an extended period of time. These discoveries happened in widespread different areas and were used for different things. Degrees Celsius is still very commonly used for some scientific measurements. Okay. Why? That's what they had when they made those observations. And so that's the system they've used. Could it be adapted to Kelvin? Yes. Will it be? No. Too many old, dead people with lots of momentum. Okay? Preventing changing those units. So we end up sticking with different calculations that involve each of those temperature ranges. Okay? To do your conversions, we've got three different conversions shown up here. That very first one, degrees Celsius times 9 divided by 5 plus 32 will get you your Fahrenheit values. Isn't that a lovely calculation? Okay. How many of you think I've got that memorized? How many of you are abstaining from this vote? Or how many of you think I don't have this memorized? Only 2 of you think I don't have it memorized. I have no clue what that number is. And I have to look it up every single freaking time. Okay? But that's largely because I have no need to convert between Celsius and Fahrenheit. Okay? For the sake of this class, you probably won't need it either, except for the 1 or 2 occasions where you're asked to calculate it. Okay? Since I don't expect you to go through and write down or have that memorized, I will provide you that first conversion. Degrees Celsius over to Fahrenheit. The next one is the same thing as the previous equation. All we've done is rearrange the equation to solve for degrees Celsius. I will not give you that one. Okay? But I expect you to be able to do the algebra to solve for it. Okay? It's not that difficult, right? Last one. I will expect you to memorize that one. Okay? Everybody seems to ask this, so let's preempt this. Our degrees Celsius to Kelvin conversion, we take our degrees Celsius and you add 273. You'll notice I wrote 0.15. Why did I write 0.15? There's some things that you just have memorized, right? Okay. How many people know what pi is? What was that number you said?
3.14159.
Okay, how many people remembered that many digits? Okay, like 2 of you. Okay. Why did not the rest of you? Because you decided it wasn't important. For some stupid reason, I've memorized Kelvin as 273.15. Okay. What do you need to remember? 273, and you're good.
But that gives you
Okay.
a different value.
So it does not give you a different value. What does it give you?
0.15 is the end of your new answer.
A different significant figure. Does the significant figures matter into the calculation? Well, that depends what your degrees Celsius is. Okay. More than likely, your degrees Celsius will get reported to the 10ths place. The 1 might become a little bit important, but it's not going to have an effect in the rounding more than likely.
Okay.
Okay. So including the 0.15 shouldn't affect your answer. Questions? How would you solve for degrees Celsius if you were given Kelvin? Subtract 273. Okay. So let's do some quick conversions here. Body temperature is 98.6 degrees Fahrenheit. What is body temperature in degrees Celsius? Now this gets back to our heat concept. Temperature versus heat. Okay? Heat measures the total energy in the system. So every particle is going to have some energy associated with it. So what we're going through and doing to measure our heat is we take the energy of every single particle, we add that up, and we get a total value. Okay? When we look at the temperature, it's the average of all of those particles. Which of those is going to generate the larger value? Heat. Okay? So heat is going to carry a different unit, number one, okay, because we aren't measuring temperature, though they're kind of related to each other. So our heat is going to be expressed in either units of joules or calories, depending, again, on English versus metric. Metric is joules, calories is English. So depending on what you're trying to do, you may be converting back and forth between either of those. Okay? If we take a look at these two containers, okay, which of those would burn you more if it got dumped on you?
B.
Oh, they are labeled A and B. Yes, B would burn you more. Why? There's more particles in there. Every single one of those particles needs to transfer their heat to you. Okay? More particles means more heat, okay? And ultimately more damage when it hits you. Okay? Even though their temperatures are the same. So they're related, but not the exact same value. Makes sense-ish? Okay. We can now come up with this concept of a specific heat. And we're going to use kind of a probably very wrong example, but it works fairly well. Okay? The specific heat is a measure of the amount of energy necessary to raise your substance by 1 degree Celsius for 1 gram of that substance. Okay?
Is that how you do calories?
So a calorie is defined as the amount of energy necessary to raise 1 gram of water 1 degree Celsius. That is a calorie. If we were to convert to joules, well, joules is now 4.186, the amount of energy necessary to raise water by 1 degree Celsius for 1 gram of water. So we can convert calories and joules through using the specific heat. Okay, and that's all fine and dandy, and if you want to do conversions, have at it and do all the conversions you want with those. They're the same kind of conversions that you would do, say, with miles per hour. It's now, instead of it being a 2-unit complex unit, it's a 3-unit complex unit. Okay? Within that, that involves a bunch of conversions, and I'm not particularly excited about it. So what I want to do is instead spin this in a way that allows us to process what specific heat means without doing a calculation. Okay? And that's where an exam question could pop up. Which of the following substances is expected to have the largest specific heat? And then we've got a bunch of different substances listed out here. I really, really like this question because it asks a bunch of different things. Number one, it asks about specific heat. Do you know what specific heat is? Okay. Number two, it's actually asking about naming of your elements. Right? Copper, different format than all the others. Okay, what format do I want it in, the symbol or the name? The symbol is going to end up being more helpful here, but that's a little bit difficult to see at this stage. So we could go through and convert that across to the symbol. Our symbol for copper is, and our symbol for carbon is, whoops. So now they're all in the same format. But now how do we decide which of these is going to have the largest specific heat? Well, this is going to come back to understanding what specific heat is. Okay, so let's repeat the process. It's the amount of energy or heat necessary to add to a substance to raise it by 1 degree Celsius. Okay? So if we envision the iPad as our material, okay, and you were to touch the top of the iPad, what we're trying to decide is, do you feel a temperature change? So if I put a match at the bottom, that match is now supplying heat. If you touch the top and you feel heat immediately, what does that mean happened? the heat transferred directly through the sample. Okay? How much heat was necessary to cause the sample to rise by 1 degree Celsius? Okay? A very small amount of heat because it directly went through the sample. You felt it right at the get-go. Okay? Kind of makes sense? So if we feel the heat immediately, we have a small specific heat. We need a very small amount of energy to cause the sample to go up by 1 degree Celsius. And that up by 1 degree Celsius is us touching it to test that temperature. What if we put the match and we had to leave it there for a really long time? That match is now supplying constant heat. And that constant heat is going into our, well, now my iPad, okay, constantly being added until you feel the heat. So we're correlating that time back to our heat in degrees Celsius and mass. So if we had to add a lot of heat to the sample before we felt a temperature change, what does that mean our specific heat is? Really, really high. All we're changing is that value up top. Remember, that was our heat term. So if I have to add a lot of heat in to cause it to go up by 1 degree Celsius, the mass didn't change, the degree Celsius, we're just looking for it to change. If I have to add a lot of heat to get the same change, my specific heat is going to be a larger value. Make sense? Okay. So the bigger the value, the better it transfers heat, or sorry, the worse it transfers heat. Okay? Can we change that around? Make that statement make a little more sense. Bigger specific heat means bad heat transfer. That was fun. What was that? Okay. Bad heat transfer, that's not very sciencey. We'll come up with a more sciencey term. Not a good conductor. Okay, also known as, we'll come to that, insulate, oh geez, not good conductor. Okay. I then heard someone making reference to metals and nonmetals. Why are you making reference to metals and nonmetals?
Because metals transfer heat better.
Metals transfer heat really, really well. So what would we predict the specific heat for our metals to be? Very, very low. We're looking at a not a good conductor, which means we're looking at an insulator, and I'm not going to try and spell that again. So we're looking at not a metal, also known as our nonmetals. Where do we find nonmetals on the periodic table? On the far right side of the periodic table. Where do we find our metals? On the left. What can we now go through and do? Match the symbols, process of elimination, find out our answer is carbon, the only nonmetal on here. Okay. Is this trend perfect? No, not by any stretch of the imagination. Is it close enough that we can approximate and come up with good guesses based off of this information? Absolutely. Okay. Phenomenal question, asking a lot of different material crammed into one big question. You will see these types of questions show up on the final as far as the style. You get something relatively straightforward, asking 6 different things for you to process. Okay? Questions about it? Okay. Conversions. This question showed up on the exam. Okay. I want to address a couple things on it. I'm not going to go through and solve it. Number one, if you take a look at your exam, it's a slightly different question than this. Okay. I made a very subtle change to it. Not a big deal. But there's a subtle change. Okay. I noticed a lot of people struggling with it. And I went back and looked at how people solved other parts of the show your work. Okay. And in those other parts, I noticed people just setting up these ratios. Okay, well, x over y must equal g over h, and solving for whatever h was. That works. That is a perfectly valid method to go through and solve a single conversion. This is not a single conversion. This is a three-step conversion. So if you want to solve a three-step conversion by setting up the equalities that you may have seen in a regular math class, that's fine. Your work is going to be probably 4 to 5 times as long as anybody else's work who set up the question the way I asked you to set it up. All of the conversion information is already given to you in the question. You just have to convert the English into the mathematical fractions to set up the dimensional analysis. One of the key important aspects of all of the show your work questions was show your unit work. You can't just say, well, 2 times 16 is 32. Yeah, I know that's 32. What happened to the units? If you don't show me that unit work, all you've shown or proved to me is that you know how to multiply 16 and 2 in a calculator. Okay. Does that mathematically get you to your correct answer? I don't care. Okay. I want the unit work. This is the type of question you can expect to see later on in the semester. For Unit 3, let's change this question around real quickly. Unit 3, what you can be expected to find is this question. Oxygen becomes water. 9 grams of oxygen. How many grams of water are produced? What happened to all the conversion factors? You have to know where to find them. That is the hard part when we move into Unit 3. All of those conversion factors are things that you have access to. You just have to realize that you do have access to them and be able to interpret the information to get you there. Keep your eye on it. Watch out for it. It's going to happen again. Chapter 4. Here's back to that same kind of idea. This next unit is going to require a lot of memorization. Okay? You're not dealing with dimensional analysis anymore. We're going to take a break from that, and we're just going to deal with some kind of history and facts about atoms and how they're built and what we can do with them. Okay? That said, it's a bunch of facts, which means you have to have those facts memorized. Okay? I asked last semester's class, after the exam average came back 30% lower, what happened to figure out what I could fix. The general response I got from the class was, I didn't study, which I thought was kind of depressing. So I'm now telling you, you need to study. You need to go through and start memorizing these facts. To give you a general idea what's happening with the exam averages, I know there's a lot of numbers up there. I went through, took a look at exam 1, and said, okay, to get an A, what was the average score? The average score came out to be a 94%. The average score for an A on exam 2 dropped to an 86%. Okay. That is a roughly 10 percentage point drop in the average to get an A. What happened to the average B grade? They started at an 82. Their exam 2 average stayed roughly the same. An average C grade, 73 to a 74. They actually improved. The average D grade, same deal, improvement. Average failing grade, again, improvement. Those of you at the top right now will fall. Okay? I'm warning you so that you start this memorization so I don't have to repeat this at the end of exam 2 saying you all fell. I'd like to keep you up at that same level. Okay? Data's there. It's those A's at the top of the class that will fall. study. Start that memorization. Everybody else in that B, C, D, or even E category, you now know that you need to work. If you work, your score will improve. Okay? Even on an arguably harder test. Okay? Questions about that? Okay. So, back to Dalton. Chapter 4's got a significant bit of history in it, because what we're looking at is our understanding of atomic structure. Okay, and we're going to look at the first half of chapter 4, then the first half of chapter 5, back to chapter 4, and back to chapter 5. Okay. If we go all the way back to kind of our origins, the early 1800s, Dalton came up with an atomic theory. Okay. And he had 5 primary tenets of his atomic theory. An element is composed of tiny, indivisible, indestructible particles. So once you have the base element, that is it. It doesn't get any smaller. We can then build off of that. Okay. All atoms of an individual element have identical properties. Okay, so they aren't different. Once I pick an individual element and I know it's, say, carbon, every other element of carbon or atom of carbon is going to have the exact same properties, no difference. Rule number 3, atoms will combine with different elements to form compounds. Okay? So we're saying if we take carbon and we mix it with hydrogen, we get a new compound that's going to have different properties than the carbon or the hydrogen separately. 4, compounds contain atoms in small whole number ratios. This is kind of the big one. If I go through and take carbon and combine it with hydrogen, I will find for every 1 carbon I get 4 hydrogens. Okay? So we get the same, or to generate a new compound, we get that exact same whole number ratio. If I somehow generate a new compound where it takes 2 carbons and 6 hydrogens, I'm going to have different properties than the first. But I will notice that I only get whole number amounts of each of those particles, or each of those elements. I don't end up with half a carbon, okay, and 4/5 of a hydrogen. Atoms can combine in more than one ratio to generate different compounds. Okay. So in his kind of summary, he then went through and built his own periodic table. And this is the image that we've got of his periodic table. Okay. So his periodic table is right there at the top. What do we got? 18, 20 elements. That was his periodic table. Notice his periodic table is also pretty exciting because there aren't any, letter symbols. Everything is a fancy little drawing. Can you imagine dealing with 100 different elements, all with fancy, stupid little drawings? Okay. He then also noticed that when he combined them, he could generate new compounds. So he listed off some of the new compounds that he could go through and make. And notice in each of those cases, he's maintaining the small whole number ratios. Okay, it's not 50,000 of one. We're looking at relatively small ratios for each of these. So he's saying from a compound, we can break it down into individual parts. Once I've got the individual parts, I can't break it down any further. Okay, is that true? No. But remember, it's the early 1800s. Give the guy a break. Okay. In the early 1800s, he was able to put this together and come up with some rules that actually applied and matched the real world fairly well. Okay. Thompson came along in the late 1800s with the next big discovery. And he ended up discovering 2 primary particles. Okay, and that's kind of interesting here. We ended up with electrons and with protons. And he noticed that these particles came from elements. So what does that state right out of the gate?
Atoms can be divided.
Atoms can be divided. Okay? An element is not composed of atoms. It is composed of subatomic particles that make atoms. Why do we call them subatomic particles? Because they're smaller than our atoms. There's our protons and our electrons.
So, compounds break down into elements, elements break down into atoms, atoms break down into
Subatomic particles. Yep. Okay. Within that, he was able to determine the relative charge of your electrons being -1 and the relative charge of protons being a +1. Okay. Getting into kind of the history of atomic structure, I find this kind of interesting. we've got roughly 100 years between Dalton's theory and Thomson's theory. Okay? Why a 100-year time span where we can't figure out that atoms can be broken down into smaller pieces? What's the technology? Microscopes cannot see atoms, much less they cannot see electrons and protons. So a microscope doesn't help you. This is a really neat discovery, in my opinion.
Was it because nobody challenged you?
Nope. It's a discovery that you probably all have in your home, hopefully. A vacuum. Okay? Why do we need a vacuum? Okay? Charge is inherently something that is bad. It is very unstable, high in energy. Our elements tend to carry minimal charge because if they're charged, they react. Okay? Very high in energy. So if I'm going to try and discover an electron, this is an electron chilling all by itself. That is now an insanely high energy particle. What is that insanely high energy particle going to spend its life trying to do? Get rid of its energy. And it can get rid of its energy by interacting with anything around it, because everything around it is lower in energy than it is. Why do we need a vacuum? In a vacuum, there's nothing around it, which then means the electron can exist for a reasonable amount of time because it never comes in contact with anything else. By removing everything, we now have the possibility to discover one of our tiniest particles, our electrons, and by correlation, our protons as well. Okay? He put this together into what is known as a cathode ray tube. Those of you that are old enough, the cathode ray tube is, yes, one and the same as our standard CRT TVs. And when you look at your old school massive TV boxes, you've got probably hundreds of thousands of these things crammed up inside them. Okay? And that's what we were using as our TV screens. So kind of a discovery of the television gave us the existence of electrons. Okay? So what was kind of neat about this? What he did is he evacuated the tube so there was now nothing inside it. If there's nothing inside it, what would happen? Build a glass strong enough so it doesn't implode. Exactly right. Nothing should happen. So what happens then if I put an electric current? So I put a big charge over here, let's say a big negative here, and a big positive here. If there's nothing inside this, what should happen?
Nothing.
Nothing. What happened? They saw light. They saw a beam shine from that negative end and follow through the tube towards the positive end. They said, well, what the heck? There's not supposed to be anything in there. Why is this happening? There's enough particles randomly in there that our electrons will spin through that process, encounter another molecule, and cause enough of an excitation that we see this light beam appear. Where there should be nothing, we now have something. This means there must be something smaller than atoms. Okay. Take this a step further, it's even more fascinating. You know the whole tree falls in a forest thing? Someone got the bright idea of saying, well, if there's nothing in there and nothing's supposed to happen and we're seeing stuff, what happens if I just cover it all up with in a cardboard box? Well, then if I can't see that nothing is happening, then really nothing should happen. And they happen to have some random photographic plates outside the box. What happened to those plates? They started to develop. What the heck? I've got nothing happening in a nothing tube inside a box. And outside of all of that, I've got photographic plates that are developing. What happened? X-rays. We got the discovery of X-rays coming out of these things. Okay? Which launched off a whole new crazy research and what's going on with these different forms of energy. Where's light coming from? Where are X-rays coming from? What are electrons? What are protons? And trying to come up with a theory of what are now new atoms can be. All right? So this is where Thompson, read Thompson, important name, went through and theorized what happened with our atoms. So we said Dalton's theory that we can't subdivide our atoms down clearly is wrong. Because in a container of nothing, I've now found something, and I know that something is charged. Okay? So he's discovered these negatively charged species that he's noted as electrons, and positively charged species he's noted as protons. Why would he need to find both?
Without them, you would figure out the mass of atoms.
Not quite. We said negatives are insanely high energy. Okay? Super, super reactive. If we look at general life, do we see these super, super reactive things? No, why not? What are these super reactive negative things interacting with? Super positive things to neutralize and cancel that charge. If everything was negative, everything would be high energy. Okay? So we've got this now theory that we have negatives and positives. Because he was better able to isolate the negative species, he went through and came up with this theory that we've got this kind of sea that is our atom. And within that sea, it is generally positively charged. And we drop a bunch of electrons inside it. So if we've got our proper conditions, we can force the electrons out of that sea, and then we can monitor our electrons. Okay? He referred to this as the plum pudding model. Okay? Our electrons are plums floating in a pudding of positive charge. Okay? When he went through and dealt with his experiment, he could really only calculate the mass to charge ratio. He couldn't nail down the exact charge of either the proton or the electron. Okay? I like to mention this one, even though it's not mentioned in your textbook, just because of the sheer science and dedication that went behind this. We've got this group of two people, or primarily two people, Millikan and Fletcher. Millikan is the one that gets credit for this discovery. Okay? And he was ultimately able to discover the exact charge on an electron in 1911. Okay? And so we've got the result down at that bottom, that crazy weird number, -19. C is coulombs, which represents charge. Not a big deal, so don't stress on the number. What's more important is looking at the experiment. Okay? Number one, well, actually not even number one, let's just go through and look at the experiment. So what they did is they took a cardboard box. For that cardboard box, probably a little bit fancier than that, they took some oil and they sprayed the oil into the cardboard box. Okay, what is that oil then going to do? Okay, it would absorb if it contacted the box, but what if it doesn't contact the box? It just kind of falls down. Okay, and it would float down through that chamber. Well, at the bottom of the chamber, they cut a tiny little hole, single little hole. Okay, most of the time when they spray those oil droplets, where do the droplets go? Most of the time? Most of the time they go anywhere but the hole. One time out of maybe 1,000, an oil droplet makes it through that hole. Okay. Once it makes it through that hole, it is now between two charged plates. One side's positive, one side's negative. At the end of that charged plate, we've got a microscope with some guy staring at what is presumably in a completely empty space until randomly, drop! And he immediately starts dialing the electric current. Okay. Why dialing the electric current? That oil droplet is carrying charge. That's one of the things that happens when you spray it out of a bottle. It picks up a charge. They can then dial in the electric current to cause the oil droplet to levitate. As soon as they've got this oil droplet now sitting stationary within that electric field, they now have a sum of two different forces. One of those forces is due to the electric field causing the droplet to levitate. What's the other force? Gravity. They can measure the size of the droplet, determine the mass of the droplet. They now know the downward force due to gravity. They know the upward electric current generating that levitation. They can then back calculate the charge on that droplet. Once they know the charge of the droplet and its diameter and the mass of the species, they can actually determine the charge on a single electron. Okay? So again, let's repeat this. We've got oil droplets spraying. Randomly, 1 in 100 chance, hits the hole, falls through the hole. As soon as they see this droplet pass through the hole, they start spinning an electric dial fast enough to hope that they can get the little oil droplet to levitate. Once it is now levitating perfectly, they can take all these measurements and then go through and then do these calculations.
So is this saying that, are you saying like, because you said 1 electron, so does one of those oil droplets only have 1 electron in it?
One of those oil droplets will carry a particular charge. So they have to do other calculations that go with it. It's not just going to be 1 electron. Okay? It'll be a variety of electrons. So they have to go through and run this experiment probably hundreds of times. Okay?
How do they find out like how many electrons are in one of them?
They can plot the size of the droplet versus what they're calculating for the charge. Okay?
This is very tedious.
Very, very tedious. Okay? And the whole point is just to figure out the charge on that electron. So through that entire process, you've got somebody looking through the microscope. Who's the name of the person looking through the microscope? Fletcher. Who got credit for this discovery? Millikan. Why?
Mrs. Idea.
It might have been. That's an interesting one. Millikan was probably the professor in charge of the research. Fletcher was the graduate student being told what to do. Who gets credit when it comes to science? The professor. Who does all the work? The students. Welcome to science. Okay. That said, once Fletcher's now graduated, he becomes famous and he gets tons of money on his own. Okay? Because he's been a part of this project, he carries some of that namesake with him. Okay? But the official credit goes to Millikan. Okay? Kind of a neat little history thing there about science and some of its inequities. If we push this further, okay, so now we run into Rutherford and his model of the atom. Okay, and I like to go through and look at our Thompson model and said, okay, Thompson said we've got the sea of positive charge with our electrons sitting in it. Okay, which means there's really nothing of any substantial mass within an atom. We just have this kind of free-floating nonsense. We determined that our electrons are super, super tiny in mass, and the protons just kind of exist around. We don't have any physical aspect to them. Okay. I like to go through and think that Rutherford looked at this and said, that's not true. Okay. I don't believe this model to be true. So he went through and designed an experiment. Okay. And in this experiment, what he went through and did is he took some alpha particles, and likely was, again, a student of Rutherford's. So alpha particles are a very high energy source of radiation. They have a fairly sizable mass associated with them. And then he took a thin sheet of gold metal, and he fired the alpha particles at the gold sheet. If Thompson's model is correct, what are the particles going to do? They're going to pass directly through the sample. There is nothing within that, or within the gold foil, that's sizable enough to cause those particles to deflect. We've got some very high energy particles coming at this, such a thin sheet, there's no way that those alpha particles should do anything except pass straight through the gold foil. Okay. Why might I think that Rutherford says Thompson's model's wrong? If he agreed with Thompson, he's going to change the design of the experiment. What he's got on this outside perimeter now is a detector. Just like our photographic paper. When an alpha particle hits it, it changes color so we can acknowledge that a particle hit that space. If Rutherford believed Thompson's model to be true, he would probably have put his detector paper immediately behind the gold foil. Why?
Because the particles will go through it anyways.
The alpha particles would go straight through. He would end up proving Thompson's model. The particles pass straight through. They directly hit the backside of it as seen by the detector. He instead has his detector all the way around. Okay. So good science or doesn't like Thompson, either way you want to look at it. Okay. What happens when he went through and then fired the alpha radiation at it? Well, most of the time, the radiation passed straight through the gold foil. Okay. And we noticed a detection at the back of it. And we saw some slight deflections. We know matter has a mass associated with it, but we've picked such a thin piece of matter that we wouldn't expect much deflection. So we get some deflection, but not much. All of that still supports Thompson's model. What doesn't support Thompson's model are the particles that are almost, or the readings that are almost a complete reversal in the direction the particle is moving. If Thompson's model is true, when I fire this now massive particle at the gold foil, it should pass directly through and do nothing else. And yet some percentage of the time, he's noticing that we're getting hits completely on the opposite side of the gold foil of where it should be. What does that mean is happening in the gold foil? It's hitting something. Something is present in the gold foil causing our alpha particles to bounce backwards. Okay? That something has to have some mass because it is stopping a very high energy alpha particle from passing through the sample. Okay? So our alpha particles have energy and they move incredibly fast, so we now know we have something massive in our gold foil. Most of the time, though, it goes straight through. Okay, one more bit of information comes out of our alpha particles. Alpha particles carry a positive charge. What if the massive thing was negatively charged? What would happen as the alpha particles went screaming into the gold foil? They would stick like Velcro. Those opposite charges are trying to neutralize. So what does that mean that massive thing is? Can't be negative, because then it would stick. It's got to be the same charge as our alpha particles. It has to be positively charged. So with this data, Rutherford now concludes that we don't have Thompson's model of a plum pudding, but we now have the existence of a nucleus. Okay, which I'll just write in there. Don't have it nicely put in. Rutherford now states that we have a nucleus where all of the protons are collected. Okay. That's a really important conclusion. We have a nucleus where we now have all of our protons. Does anybody see an issue with collecting all of our positively charged species in the same location?
They should all reflect off each other.
Positive charges are the same. They want to repel. So while Rutherford brought forth this model, he then said, well, there has to be something else present to keep those protons stuck there. So he now postulates the idea that there's something else there, and that something else does not carry a charge. So he calls it a neutron, neutral. Right? He doesn't have direct evidence for it. He's just postulating that there has to be something there holding all of the protons together, okay, in that nucleus. Right? All of this hinges on this particular source, the alpha particles. What are alpha particles? They are high energy particles sourced from where? We just go to the alpha particle farm. They come from radioactive isotopes. Certain isotopes will release alpha particles when they decay. Okay? So some elements will eject these high energy particles. Okay. The clutch on this experiment is that we have to ensure that that is a consistent source of alpha particles. Because if it fires something else, that can now potentially change the gold foil. Which then means when I fire the alpha particle at it, am I hitting gold foil anymore? No, so I might be getting bounce back because I'm firing screwy things from my sample. So that means my source of alpha particles has to be incredibly pure. Okay. Where did he get the alpha particles? Got them from radium. Okay. Purification, purified radium. Very radioactive source, ejects these alpha particles at relatively high frequency so that he could run this experiment. Okay.
How do you control which direction they're going?
If you look really carefully at that box, it says lead. What is that lead doing?
Deflecting?
It's keeping all the radiation inside except for one tiny hole where the radiation can now pass out. We have to have pure radium. But it's ejecting radiation. What do you know about radiation? It's really bad and dangerous. Okay? So somebody had to go through and risk their life to come up with a method to purify it.
They didn't know radiation was bad at that point, did they?
That might be true. They didn't think it was as bad as it was. Okay? They definitely knew it was bad. The next issue with this is that as soon as it ejects that alpha particle, our sample changes its properties. It's no longer that same material as our radiation source. So we have to make sure that radiation source is incredibly pure. Where do we find pure elements in nature? We don't. Someone has to go through and purify them. This is an incredibly important discovery and a mechanism by which to purify this sample. A lot of science is now based off of this discovery. Okay? That discovery being so important, you might think that the person that discovered it would likely stamp a patent on it. Because what happens when they stamp a patent on it? They get money for everybody else using their research. But at the same time that they get money, now nobody can use their research if they don't have the money to do it. The person that discovered this purification scheme did not patent it intentionally because they wanted science to grow as a field. Okay? You need to have access to that information. That's why we have schools. We want to have access for everybody to learn. Okay? So this person's pretty impressive that they went through, did this discovery, risked their lives, put it all together. Okay? Who was it? Madame Curie. Okay? So after all this issue, we're looking again, turn of the century, early 1900s, risked their lives, didn't patent it, and is a woman. Okay? What was the right to vote? There wasn't one. What was any right to women at that time? There wasn't one. And yet somehow this woman was able to do all of this and then was so good-natured to then release that information for public access that we can now understand something about atomic structure. Okay? This is an amazing discovery, an amazing person for going through and doing this. Such an amazing discovery that in our home country, France, so every country has a group, okay, of national scientists where they get together and say, oh, you're a good scientist, let's give you an award. Such a great scientist that the National Academy of Sciences in France denied her access because she was a woman. Okay. At least there were other industries or sections of science that admitted how awesome she was, and they gave her a Nobel Prize. Not once, but twice. 2 people have ever received a Nobel Prize, more than once. One person has only received 2 Nobel Prizes in scientific fields. That was Curie. Okay? It is amazing what she was able to do within that time frame and those utensils and still be able to do amazing, amazing science. Would highly encourage you to go through and take a look at the history behind that. That is one of the things that drives our understanding of a nucleus. Without that radiation source, we don't understand a nucleus. Is a nucleus important? Yep. That kind of drives all of our scientific discoveries since then. Okay? We'll pick up there on whatever the next day is, Thursday.